Welcome students. Today topic is Mux. Mux means multiplexer, or you can say this will be the selector switch. Selector switch logic diagram. Okay. It's mainly used is in the transmitter station where there are many signals to go for a single receptor, but out of many signals only one signal will go to the only one receptor available. That will depend on the selector signals. Okay, so here block diagram of Mux, we can say this will be the block diagram of Mux, and there are number of input signals I0, I1 up to in minus 1. It means there are n number of input signals. These are what? Input signals. Okay, and there is only one output signal. There is only one output signal. Out of these n input signals, only one input signal will go to this output, because output available is only one. Okay, so out of these n signals, which input will go to this output, that depends on select signals. Select signals, these select signals named as S0, S1 up to Sm minus 1. Okay, so value of these signals will determine which input signal will go to this output. Okay, now how many these select signals we have to select here, how many signals will be there, that depends upon 2 raised to power m is equal to n. Okay, this n value is this. N is the number of inputs and m is the number of select signals, because this is 0 to m minus 1. So total m values of these select signals, and here inputs 0 to n minus 1. So n number of input signals. Okay, so this will be the formula 2 raised to power m is equal to n. Okay, for n number of input signals, there will be m number of select signals. These are select signals. Okay, now one more signal is there, one more controlling signal is there, that is named as G. Okay, and this signal will be such type of connection, This signal is known as enable or strobe signal. Okay, enable or strobe signal, right? And this multiplexer, or as an acronym or in short form, we say Mux, or simply we can write multiplexer. So this is n is to 1 multiplexer. Okay, as a simplified example, we can write here the example of 4 is to 1. Firstly, we will understand it by very simple example of 4 is to 1, because this is a general example of as n is to 1, but we understand it by very simple example of this Mux as 4 is to 1. be the case? 4 input signals and 1 output signals. So we are discussing here 4:1 Mux. Okay, so this will be the block diagram of 4:1 Mux. This will be the block diagram of 4:1 Mux. Okay, 4 input signals, 1, 2, 3, 4. Okay, I0, I1, I2, I3, 0 to 3. So it means 4 input signals and 1 controlling signal is also here. So G as a controlling signal. Okay, you name it as stop signal or enable signal, right? Okay, then how many select signals will be there? Because 4 inputs are here, so it means 2 raised to power 2 is equal to 4. This is the value of m and this is the value of n. It means here 2 select signals will be there. Okay, S0 and S1. Okay, these are select signals. Select signals. Okay, now what to do? This drop signal have bubble for in going to this mux. This has to face bubble. It means this will be known as active low signal. Okay, this will be known as active low signal. What is the purpose of this drop signal? This drop signal is controlling the functioning of all this mux. Okay, if it is 0 here, then this whole circuit will be activated. Okay, will be activated because this is the enable signal and this is active low signal. Here if it is the value or having 0, then this block will be activated as a mux. But if here it is a value, it has the value of 1, then this mux block diagram or this mux logic circuit will be disabled. Okay, so here truth table of this 4:1 mux. Truth table. Okay, what will be the truth table? Select signals, output. Okay, here we have also to draw a output, that output. Okay, now select signals, output. Select signals S1, S0. Okay, and output signal is there. Okay, now G stop signal is also here. Okay, now 2 select signals. So how many combinations are there? 0, 1, 0, 1. 0, 0, 1, 1. Okay, now here if it is 0, 0, then output will be I0. Okay, if here it is 0, 1, then output will be I1. If the combination is 1, 0, output will be I2. If the combination is 1, 1, output will be I3. Okay, now here value of G will be 0, 0, 0, 0 for all these combinations where this program has an active function. Okay, so if G, value of G is 1, then no matter what the value of these select signals, and here value will be low. Okay, so if the value of this G is 1, then whatever value you can give to these select signals, that will not affect this output. This will permanently be in low state. Okay, so here what will be the logic expression? Logic expression. Logic expression of this 4:1 Mux. So logic expression, as we write output as a y. So y will be written as S1 S0, as by this truth table. By this combination 0 0, output will be I naught. So S1 value 0, S naught value 0. So we can write here S1 bar, S naught bar, then I naught. Actually we are writing sum of product form. Okay, so this is the first product form, this is the first product term, and we are doing the sum. And for the second combination, value of S1 0, S0 1. So it means S1 bar, because S1 value 0, so S1 bar, and S0 value 1, so S0. Okay, and then I1. Okay, plus next product term, the next combination. Okay, for that value I2. So S1 value 1, S0 0. So it means S1 value 1. So S1 as it is. S0 value 0. So S0 bar. Okay, then I2 plus, then next combination, S1 value 1, S0 value 1. So it means S1, S0, I3. Okay, so this will be the SOP form, sum of product form. These are product terms and we are doing some of these product terms. Okay, now what will be the role of G here? Strobe signal. So we multiply all this SOP form with G bar. Okay, G bar, right? So okay, and what is the role of G here? If we put 0 value here in the place of G, then 0 bar, it means 1. Then this SOP terms will have some significant role. Okay, so this will be the logic expression of 4:1 microprocessor. Oh, sorry, multiplexer. Okay, then now we realize the logic diagram of this mux, because this is only the block diagram. Okay, now we will draw the logic diagram of this mux. Okay, we draw this. Please remember this truth table. Okay, and this logic expression. Okay, now we will draw the logic diagram of this 4:1 mux. Okay, because there are 4 product terms. Okay, in SOP form there are 4 product terms. So 4 NAND gates. We are realizing the logic diagram of mux in the terms of NAND gates. Okay, it will be very simple to draw logic diagram in terms of basic logic gates. So we are using only universal gates, NAND gates. Okay, so 1 2 3 4, because there are 4 product terms. Okay, first term I naught will be the first input to first NAND gate. then second NAND gate I1, then the third NAND gate I2, then the fourth this I3. Okay, now role of select signals. Okay, now role of select signals for first product term S1 bar, S0 bar, I0. Okay, what was the first product term? S0 bar, S1 bar, I0. Okay, so we use S1 bar, S0 bar. Okay, then next term S 1 bar, S0, I1. Okay, so two more inputs. So S1 bar, S0, S1 bar, S0. Okay, now third product term. Third product term we write as S1, S0 bar, I2. Okay, for I2, two more inputs, S1, S0 bar. Okay, now fourth term S1, S0, I3. Okay, so two more inputs here. So these are S1, S0. Okay, so now output of these NAND gates will be the input of one more NAND gate. This. Okay, this, and this will be the output Y. Okay, this what we follow the technique of realizing the logic diagram as according to logic expression. Okay, by using universal gates, NAND gates. Okay, now this will be the final output here. Y. Now what will be the role of G? Strobe signal. Okay, then strobe signal. Here we take this strobe signal G. Okay, because this will be the active low signal. So G bar. Okay, G bar. We take G bar and connect as input to every available NAND gate. This, because if we apply 0 here, then 1 will go to each and every NAND gate. Okay, because if we apply 1 here, then 0 will go to each and every available NAND gates. And you know, if only one value of NAND gate, input value of NAND gate is 0, then there is no any role of all other inputs. Okay, so this is the enabling signal G. So here it is the role of G. So this is the selector switch, this is the multiplexer, and we discuss very simple example of multiplexer as 4:1. Okay, so here we see the application of this mux. Okay, by having some very simple example how to implement this mux in our any electronics problem, how we use this mux. Okay, we take some example. Okay, F, A, B, C, D is equal to summation small m 0 to 3, 6, 8, 9, 12, 14. Okay, as we implement 4 is to 1, so in the same way, in the same symmetrical way, we can implement 8 is to 1, 16 is to 1. Okay, there are many types of ICs which already have in our market, as there is given a complete table of these ICs as 74152 as 8 is to 1 mux, and 74150 as 16 is to 1 mux. Okay, and 74157, here in this IC there are quad 4 2 is to 1 mux. Okay, so by using any such type of IC of mux, we can implement, we can solve this type of problem. There is a problem given in this form, and it is saying that you have to implement this function by using a multiplexer of 16 is to 1. So here we draw a block diagram of 16 is to 1 mux. 16 is to 1 mux. As we implement 4 is to 1 mux, in the same way this will be the 16 is to 1 mux. Because in 4 is to 1 mux, there are 4 NAND gates. In 16 is to 1 mux, there are 16 NAND gates. Okay, so in this IC having pin numbers as 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 and 15. 0 to 15, it means inputs 16, okay, and only one output. Okay, now here summation small m is equal to in bracket 0, 2, 3. Okay, it means there are product terms. Okay, there are product terms having mean terms. Technically we say mean terms. Okay, so for 0, whichever the decimal equivalents are given, we connect to these decimal equivalents as logic 1. Here in the straight to 0, then 2, then 3, then to 6, then connect to 8, then connect to 9, then connect to 12, 14, 12, 12 here in the straight way to 12, then to 14, okay, to 14. Okay, and all other pin numbers just connect to 0 as this 1 straight to 1, logic 0 to 1, and all other remaining pin numbers will be connected to 0. This connect to this 5, okay, and 7 and 10, then 11, then 13, then to 15. Okay, this is a very simple implementation by using 16 is to 1 mux. If you have been given such type of problem, we can write here as a complete problem as implement using mux. Simply here may be written as a mux, or specifically written as 16 is to 1 mux. So here will be the how many select signals will be there? Okay, 1, 2, 3, 4. Okay, in the same formula, 2 raised to power 4 is equal to 16. Here it will be the value of m. Here it will be the value of n. Okay, so S3, S2, S1 and S0. Okay, and in the same way, enable signal G will be connected just like in same way. G stops it. Okay, and this is the implementation of this type of function f a b c d is equal to whichever the midterms are given 0, 3. Just connect all these given midterms straight to the logic 1, 0, 2, 3, 6 out and remaining midterms to logic 0. Okay, and this is a very simple implementation of Mux, right? So if you want to implement some other take example as you say if we want to implement 8 is to 1 Mux. Okay, if we say implement 8 is to 1 Mux, it means then firstly what will be the number of select signals? 2 raised to power 3 is equal to 8. Okay, so how many NAND gates will be there? Okay, NAND gates 1, 2, 3, 4, 5, 6, 7, 8. Okay, now NAND gate. Okay, all these gates are NAND gates because NAND gates are being used as universal gates. Okay, okay. Then to first NAND gate, first input I0, second input I1, third input I2, fourth I3, then I4, then I5, then I6 and I7. Okay, now 3 inputs will be there as according to the select signals. First 1, 2, 3. Okay, and what will be the values of these 3 signals? As in the same way, S3, S2, 3 signals. No? Okay, S2, S1, S0. Okay, so for I naught, what will be the value? 0, 0, 0. Okay, if we write the whole combination, then 0, 1, 0, 1, 0, 1, 1, 2, 3, 4, 5, 6, 7, 8. Okay, 0, 0, 1, 1, 0, 0, 1, 1. Here 0, 0, 0. 4 times 0, 4 times 1. If because we want to collect all the combinations now. So this is a technique to collect all the combinations. Firstly 0, 1, 0, 1, 0, 1, then 0, 0, 1, 1, 0, 0, 1, 1, then 0, 0, 0, because 1 times 0, 1 times 1, 2 times 0, 2 times 1, 4 times 0, 4 times 1. Then if the select signals will be 4, then 4 times 0, 4 times 1. Oh sorry, 8 times 0, 8 times 1. In this way, we can collect all the combinations. Okay, firstly 0, 0, 0. It means S2 bar, S1 bar, S0 bar. Okay, then for this 0, 0, 1, it means S2 bar, S1 bar, S0, this in this. Okay, then 0 1 0, 0 1 0, S2 bar, S1, S0 bar. Okay, for third, because we can write again output as I0, I1, I2, I3, I4, I5, I6 and I7. Okay, so here for I1, I2 and I3. For I3 combination, okay, right. For I3, 0 1 1, okay, S2 bar, okay, S1, S0, okay, I for I3. Oh, sorry, for I3, right, this, okay, okay. Then for I4, S1, so S2, then S1 bar, S0 bar. Okay, for I5, S2, S2, S1 bar, S0. Okay, for I5. Then for I6, S2, okay, S1, S0 bar. Then for I7, S2, S1 and S0. Okay, now connect the output of all these to one more NAND gate. This will be final output. Output of these connected to input of NAND gate. Okay, this in this way. This is a very simple strategy to implement any type of mux. As we implement 4 is to 1 mux, in the same way we are implementing 8 is to 1 mux, and you can do your assignment as a 16 is to 1 mux. Okay, now here we will also show the role of G strobe signal. Okay, G passing from inverter, just connect as an input to each and every NAND gate in this way. Okay, I hope you understand the basic concepts of this mux. Thank you so much.